and that is the aqueous humor. This is between the cornea and the lens. Let me pull up that picture that I'd shown last time, and I sent this out on Moodle. Between the cornea and the lens. I'll bring that back up in just a second. And so it is going to be right here, I think. Yeah, between the cornea and the lens. Is that right? That's correct. It's right here. The aqueous humor. And then we also have, this replenishes and drains. We talked about this in the pressure chapter. Because if you get too much of it produced, or if it's not draining, then you can get a too high of a pressure. And excessive pressure is called glaucoma. Either that drainage is blocked in some way, or you're producing too much of this fluid that's in the aqueous humor, which, by the way, it mentions in the book that this is mostly water, and you can tell that because the index of refraction is very close to that of water, so it's mostly water. The aqueous humor, and then we also have the vitreous humor. This does not drain or replenish. It's not replaced, which I find kind of remarkable that like this part of your eye has been around ever since you were born. Isn't that cool? Yeah, so it's not replenished. And this acts to help, it's the rest of the eyeball, it acts to help keep the shape of the eyeball. So it has a number of other purposes, but one of the primary purposes is to help keep the shape of the eyeball. All right, so those are the two liquids. I'm going to show you a little video. I don't think that we're going to get to the assessment today, but there'll be plenty of time after the final to take it, because the final is just going to be a normal length test. Okay? So I'm sorry for that. I'm pretty sure that we're not going to have time to get to it. This is our last class, yeah. Let's see. I have a video called Anatomy and Function of the Eye that just talks about how the eye works. Most refraction occurs at the air-cornea interface. And if you, I don't know if you noticed in the video, but they showed this in the diagram when they showed the light going through the cornea and into the lens. And the reason that most of the refraction occurs here is because the difference in the indices of refraction is so much greater. Once the light actually gets into the eyeball, the indices of refraction don't change that much, so the light's not going to bend that much. So the lens, for example, is not that much different than the surrounding fluid. So the light isn't going to bend that much. The lens is really just sort of fine-tuning the direction of the light, with most of the refraction occurring at the cornea interface. Let me show you on this picture, this diagram of the eye that we have. So we get, if we have light that comes in, notice here that it's going to bend mostly right here. But then when it comes into the lens, it'll just bend a little bit until it goes back to the fovea, or in that portion of the retina. So most of the refraction occurs right here at the air cornea interface, just because the index of refraction, here is like n equal 1, but in the cornea, I think it's like 1.4 or something, the index of refraction. So it's quite a lot more different than inside the eye. And by the way, you don't need to know this number, but just to give you some reference, inside the eye, the index of refraction is very close to 1.3, which is about that of water. It doesn't change very much. All right. Yeah, that's all. Let me just put this in writing. I said this earlier, but let me just say it again. The index of refraction that's in of the two liquids, the aqueous and the vitreous humor, is very close to that of water. So we could ascertain correctly that it's mostly made up of water because it has an index of refraction that's mostly that of water. That's, by the way, is a very nice way to determine unknown gases and unknown liquids, is to measure their index of refraction. I think I might have mentioned this earlier. And you can determine them based on that index of refraction. All right, let's look at the difference between the eye and the camera. There's really no other optical instrument like the eye, because it's just not very practical for us to create an instrument like the eye, meaning that the eye does something different than other instruments. A camera, when you're focusing on objects at different distances, a camera, you're going to change the position of the lens. Right? However, with the eye, you can't change the position of your lens. You can't pop your lens in and out of your eye. You can't change its location, but instead you change the focal length of the lens. Let me draw a figure here and show you what I mean. Let's say that we have your eye here. This is your eye. I can treat that cornea and lens just as a single convex lens, and it has a certain focal length. All right? My image distance for my eye is going to be this distance. This is my image distance. Did we call this DI? I think we did. Is that right? Yeah, so this is my image distance, DI. That's fixed. So with the eye, the image distance is fixed. Because you can't change the shape of your eyeball when you're looking at things. You can sort of a little bit, and that's why you squint when you're having trouble seeing things, because you can sort of squeeze a little bit, or maybe squeeze your cornea just a little bit when you're trying to see something. If you can't see very well, you can squint. But overall, you can't change the shape of the eyeball. Right, so for the eye, the image distance is fixed. So in order to see things that are at different distances, you adjust the focal length. So the focal length changes. All right, so I'm going to draw some rays here coming from something that's very, very far away. So if I have something at p equals to infinity, something that's really far away, then my light rays are going to come in like this, and they're going to focus at the focal point. And so in this case, if my object is very far away, my focal length is equal to the image distance. So when p equals infinity, the focal length equals the image distance. Because I always want my image to form on the retina, at the fovea, or where most of those rods and cones are located, at the back of the eyeball. Right. Now, however, if p is shorter, so when p is small, my focal length is less than the image distance. Let me show you an example. Let's say, I'm going to make this my optical axis. It goes down through the center of the lens. Let's say that I have an object right here. Remember I showed you those two rays that you can draw? Let me go ahead and do my focal points. These are going to be my two focal points. I can draw a ray that's parallel to the axis, and then through the focal point. And then I can draw the reverse of that ray which is going to be through the focal point and then parallel to the axis. So here, my rays cross, and they cross at the back of the eyeball. So this is still my image distance, but notice that my focal point is now shorter. So if I'm looking at something that's really far away, like the back of the room, my focal length is equal to the diameter of the eyeball. But if I'm looking at something that's closer, like my finger in front of my face, then my ciliary muscles inside the eye, they squeeze down on that lens, make it fatter in the middle, and that makes to have a shorter focal point. Right? So they squeeze this lens down and bring that focal point from here up to here. Right? So that's how the eye works. Image distance is fixed, but the focal length changes. That's very different from a camera. Because a camera, here we have our film. This is like the retina. The film is going to be where your image is. And here we have our lens, right, that has a fixed focal point. So for a camera, the focal point is fixed. It's just not really practical to make a lens that changes shape. It's very difficult, actually, to make a lens that changes shape in a very described way. The eye is different, obviously. So the focal length is fixed, and the image distance changes. All right, so if I'm looking at something really far away, I have light rays that come in parallel. They will focus on the film, which will be located at the focal point. So that would be the focal point. But if I wanted to look at something that was nearby, what would I do to the film? Would I move the film to the left or to the right? Would I move the film further away from the lens or towards the lens? What do you think? If I'm looking at something really close, do I move the film away from the lens or towards the film? It is away. Let me show you. So because if I'm looking at something that's close, let me draw the diagram here like we did before. I'm looking at something now close. Here's my focal point. Here's my object. I can draw a ray parallel to the axis and through the focal point. Remember, my focal point doesn't change here. Or I can draw a ray through the focal point and parallel to the axis. So my image is going to form back here. So I want to take this film and move it back here. Or you can take your lens and move it out. Here's the idea. You want to increase this distance so that the image is on the film. They work very similarly. The difference is that the image distance for the eye is fixed and the focal length changes. For the camera, the image distance changes, but the focal length is fixed. Just because of glass lens, you can't change its focal length. Right, and so when you're changing your camera, when you're zooming in, the lens moves in and out. What it's doing here is it's moving the film or the CCD or whatever it is that you have in your camera so that it's at the image distance where the image is forming. Okay, you with me on this? Okay. All right. I think it's kind of cool, actually. All right. A couple more things. We're going to look at the near and far point, and then a few problems that we have with vision. So the near and far point. These are just the nearest and furthest points where you can see things. So this is the nearest point where you can see things. This is different for different people. It gets longer as you get older, but you can illustrate this. You just take your finger and just move it towards your eyes, and then where it goes fuzzy, that's your near point. So your near point for most people, our age or your age or whatever, it's going to be about 10 centimeters. I have pretty good vision actually, so my near point is pretty close. It's about 10 centimeters still. But as you get older, your near point will move out. Like that's why you see older people holding their books out this far, because their near point has moved further. All right, so it's the nearest point where you can see, and the far point, of course, is the furthest point where you can see. All right, now your near point typically is 10 to 100 centimeters. Your near point is 10 to 100 centimeters. 100 centimeters would be pretty bad, but 10 centimeters right about here, you can see your finger, or 100 centimeters, like a meter away from your eye. That would be the near point, the closest that you can see something. That would obviously need some sort of correction, right? And then the furthest point where you can see an object, ideally this is going to be infinity, so you can see as far away as the light will reach your eye. Yeah. This comes up when we're talking about problems with the eye, nearsightedness and farsightedness. Can I go down from here? Because that's how we'll characterize these things for nearsighted and farsightedness. Nearsightedness. In this case, the image forms in front of the retina. This means that your eyeball is just too long. So the eyeball is too long. So just to exaggerate it a little bit, your eyeball would look like this. Right? And then light rays coming in, your focal length can only get so long on that lens. It's sort of driven by how thin it can get in the middle. And so when these light rays come in, they're going to form right here. They'll focus there. And so your image, when these light rays go back, they'll produce a very fuzzy image on your retina. And so your eyeball is too long. Just physically, it's too long. And that causes the image to form in front of the retina. Now what this means is that you can't see very far away things. Right? So nearsightedness means you can see nearby things or you cannot see far away things. So you can see nearby things. I'll just leave it at that because that helps me to remember it. So nearsightedness means you can see nearby things. And then farsightedness would mean you can see far away things, but not the opposite. You'll follow me on this? So you can see nearby things, but not far away things. That's nearsightedness. You can use a diverging lens to correct this. So if I put in a diverging lens right here, it will correct this. And it corrects it by causing the light rays to actually go out a little bit before they go into your eye, and then they will actually focus at the retina. You can tell people that are nearsighted because their glasses will actually make their eyes look smaller. So go home, if you're nearsighted, look in your mirror and put your glasses on and see your eyes, and then take them off, and your eyes look a little bit smaller, right? Because you have these diverging lenses. You can also tell most of your lenses today they're made thin, but if they're not made thin, you can see because they'll be thicker on the edges than they are in the middle. Yeah, are you nearsighted, Ben? Yeah, so you can see them sort of protruding on the edge. Or they also makes you look like you have small eyes, beady little eyes. I like to tell my wife. Okay. She's very nearsighted, by the way, but she has these very thin lenses, so you can't tell just from looking at the lenses. Okay. This is also called myopia. You don't need to know that, but if y'all probably do know this regardless. All right, let's look at farsightedness, which is also called hyperopia. Farsightedness means that you can see far away things. Or that you can't see nearby things. The problem with farsighted is not that your eyeball is too long, it's that it's too short. So the eyeball is too short. So it'll look like this, just to exaggerate it. Well, that's not exaggerated. There we go. So this would be our eyeball. Be too short. And so I can see far away things just fine because if I'm looking at something far away, the lens just has to get fatter in the middle. And it can do that just by squeezing down on those muscles. But if I want to see something that's close, I'm going to have a lot of difficulty. The light rays are actually going to cross like this, and it's going to form the image behind the retina. Instead of on the retina or in front of the retina, the image is formed behind the retina. So the image here of nearby things is formed behind the retina. All right. And this would mean also that your near point would be really big. So a person with a near point of 100 centimeters is farsighted. So the near point is large. You can tell people, well, the way you correct this is with a convex lens or a converging lens. So if you want to correct this, you just put a lens like this in front of their eye, and that works effectively to move that image into focus on the retina. And you can tell people who have a convex lens because their eye looks really big. I brought one somewhere. Oh, here it is. Y'all seen this one before, I think. But you can tell because their eye will look big behind their glasses. Or if you look at them closely, the lens will be thicker in the middle. So let's see. You might not. You see my eye? Some of you? I can pass this around if you like. You see my eyes that look really big? You sort of have to be just right. You can see it, right, Shauna? Yeah. So your eye, it's like in the movies, right? When that guy puts on the glasses and his eyes look really big. That's a convex lens. It's like a magnifying glass. You want to pass it around and try it out? So you just have to hold it in front of your eye. If you can see the person through the lens, they can see your eye. And your eye should look really big. All right, so we fix this with a convex lens. Make sure that's all I had here. Yeah, you can't see up close objects, the near point. Yeah. And then there are a couple other things. That's presbyopia or astigmatism. Can I go down from here, guys? Oh, farsightedness is called hyperopia. You don't need to know that, but if you see it elsewhere. On the test, I'll just call it near or farsightedness. These last two are age-related problems. There's a small section in your book on age-related problems, and that is presbyopia or astigmatism. Presby, it means elder, by the way. So this is a problem that you have when you get old, I guess. The first one is called presbyopia. And this is a form of farsightedness. But it's not because of your eyeball, the shape of your eyeball. It's just something that comes with age, right? So you can see far away things, but not nearby things. So that's why old people hold their books up like this to read them. Right? So farsightedness, but the farsightedness is due to the lens losing its flexibility. Right, so that lens just isn't able to contract as much. It's not able to change its focal length as well. So it loses its flexibility, and that causes you to become more farsighted. This just comes with age. There's nothing really, I don't think there's much you can do to stop this. But as I said, the eye as an instrument to last for 80 years, even though you have problems, is quite amazing because what instrument, electric instrument do you have that you use for 80 years? Yeah. I don't know. I have no idea. Do you know? Between 40 and 50? Oh, okay. Really? Is it bad? Huh. Now, my wife is nearsighted, and the doctor says that she will get less and less nearsighted, but then she'll move into becoming farsighted. I don't know if that's true for everybody, but really, okay. So that's some hope for her. She hasn't quite gone over that threshold, but there should be a day or two there where she'll have good vision. Yeah, I think so. I mean, I'm not an optometrist, but okay. So that's just due to the lens losing its flexibility, and your your near point increases. Right? It happens to everybody. So don't make fun of people that hold their books out here, okay? Because it's going to happen to you too, one day. Not that y'all do that. And then finally, astigmatism. And this is different from all the others. This is the lens has different focal points through different lines of sight. Um, so I would have a lens here, and you would get rays coming in one part of the lens, and they would focus there. And then you would get rays that would come into, let me do this in a different color. You would get rays that come into another part of the lens, say here, and they focus off here, right? And then in another part of the lens, maybe here, and they focus over here. So you just have all sorts of different focal points in the lens in an astigmatism. And this can cause for a very fuzzy image because it's not just that they're shifted off by a little bit, but you have a whole series of different focal points inside your eye. That's called an astigmatism. It's just a deformity in the lens. And you can correct this. I don't know how they make these exactly. I mean, you can grind lenses to have whatever focal points you want. But the way you correct this is you just create a lens that has different focal points, right, to counterbalance whatever the focal lengths of your eyes are. Again, I don't know how they do that, like how optometrists do that, but to correct it, correct this, create a lens with different focal points. To counter the focal points or to correct the eye. They talk about in the eye as being like a cylindrical lens, and light coming through different parts of the lens will focus at different points in the eye, causing to correct this problem with the eye lens and the cornea. All right. There were a couple other things like on LASIK and what have you, but we're going to not go over that. So those last few sections, anybody have their book readily available? Can I see it? Thank you, Reagan. Oh, she's got it. So again, just a second. Those last few little things, the other methods of vision correction and other problems, that you won't see any of that on the test. Those are the last two sections. Okay? The other methods of vision correction, that goes into LASIK and then other problems. Right, just up to astigmatism. We'll just stop there. Thank you, Reagan. What's that? Right. Yeah, we're going to stop at astigmatism. All right, guys, I'm sorry, we don't have time right now to do the assessment. It's 40 questions. It might be enough time for some of you, but not for everybody. So I'm going to hold off. I'm sorry for that. I did warn y'all that might happen, right? Yeah, okay. So that assessment will be given. You'll have it after the final. I'm going to hand back your reading quizzes, though, right now, and then y'all can go. And I did upload your